Hi, this is Bruce again with Z Group Energy. If you're already in the geothermal industry, or perhaps just curious about it, wanting to know more about it, you'll likely already know that dozens of empirical studies and subsequent white papers have been published globally regarding variables impacting geothermal reservoir pressures and return well flows. We can only touch on this vastly complicated area of underground hydraulics research here, but a brief overview may be helpful to better understand the value added to cost-effectively stabilizing geothermal system flows utilizing the sealed ZGE geothermal system. Delicately balanced steam turbines used in generation of electricity can spin in the range of 1800 to 3600 revolutions per minute. Inconsistency of steam flow, temperature, pressure, or velocity delivered to the turbine blades can damage finely tuned equipment, hence must be avoided. ZGE refers to these steam delivery inconsistencies as hiccups. Eliminating hiccups and stabilizing these various fluid elements in a below-ground geothermal reservoir, which is basically an open system, is challenging. We'll touch on just a few reservoir stabilization issues for clarification. Now, pressure equilibrium is one such critical element. Sometimes the difficulty in stabilizing geothermal reservoir pressure originates with injection well flows rather than from within the reservoir itself, and as you may know, many factors influence injection well flows. Complicating matters for power plant operators is the variance in one or more below ground factors caused by attempting to improve another factor. One step forward, a half step back, as we sometimes say. Now, some factors may include, but are certainly not limited to, is the in situ, that is the in-place geothermal reservoir, stabilized above or below hydrostatic pressures, and what effect may gravitational or pressurized injection well flows have on the existing reservoir and subsequent return well flows. For example, higher in situ reservoir pressures require higher injection well pressures, in turn impacting pumping costs. On the other hand, vertical rock fractures, when present, lend themselves to gravitationally injecting the reservoir, assumedly at a lower cost. Excuse me. Are rock fractures primarily horizontal, or are vertical fractures present? How extensive are these fractures? To what extent does the fractured production zone extend beyond the return well envelope? Geologic structure impacts how the relationship between injection wells and return wells can best be managed. Injected fluids for reservoir replenishment and stabilization can be lost to fractures extending far beyond the intended production zone. This can be costly and additionally complicate pressure stabilization of the reservoir in the return well area. Now, as another question, if reinjection fluid temperature injected into a liquid-filled reservoir is the same as reservoir temperature, and permeability between the injection bank and reservoir doesn't vary, pressures tend not to be impacted. However, when reinjection fluid temperatures are cooler than reservoir temperature, as is often the case, the mobility ratio reduces to the ratio of viscosities of the cooler injection fluid and warmer reservoir fluid, in turn reducing injection well flow in most cases with a resultant increase in pressure. This circumstance must be recognized and effectively managed by the system operator. Another issue. Over time, geothermal reservoir levels can vary. Since injection wells once drilled aren't mobile, we can't move them around. This variance in liquid surface impacts injection well performance. Now, it seems the typical issue is declining reservoir levels, but conversely, sustained injection over time may cause reservoir levels to actually rise, in turn back pressurizing injection wells, affecting well performance. Now, those are just a few issues. I don't want to go any further. We could list many, many more. We'll just go on. I think you get the idea. As you can see, without going any further, management of geothermal reservoir levels, temperatures, pressures, and return well flows comprise a complicated balancing affair, effective operation of which demands extensive operator knowledge and experience. ZGE approaches stabilization of geothermal systems in a very different, we think simpler, more controllable manner. ZGE utilizes a sealed geothermal system. You can see it there on the right. There's a page of the patent, a drawing that's in the patent. ZGE utilizes a sealed geothermal system, preferably at supercritical temperatures, to harvest heat from hot rock. Reservoir fluids are not harvested. Hence, reservoir levels, pressure, amount of horizontal or vertical fracturing, and permeable flows are all immaterial. Only temperature, i.e. heat, harvested from surrounding hot rock is critical. Therefore, drilling depth to adequate temperature is the singularly crucial element for ZGE's system, and fortunately, drilling depth is manageable. In fact, as an aside, drilling depth is now even more manageable since the Iceland Deep Drilling Project team proved its drilling capability to temperatures of 450 degrees Celsius in January 2017. Supercritical temperatures can now be reached, leaving reservoir stability as the primary system issue. The ZGE systems, and again you can see it on the left here, a part of the system anyway, the exchange chamber and some heating cylinders going down into the hot rock. The ZGE system handles geothermal system stability and operational consistency by employing clean water as the energy transfer medium within an internal sealed system, conductively harvesting thermal energy from surrounding hot rock, whether wet or dry. Pressures and convective flow rates are conveniently managed internally within a closed recirculating system. Recirculated cooler water or added fresh water exert only a manageable impact on overall operating system temperature and pressure, as the internal mass balance between heated and cooled water is strictly controlled within the exchange chamber and its sealed heat cylinders. Hiccups are basically eliminated as ability to control internally is enhanced. There you have it. The most cost-effective way to control geothermal reservoir stability, or instability as the case may be, is eliminate the reservoir. Store your heat energy at ground surface in a clean, manageable, well-insulated exchange chamber bolstered by system redundancies, all with zero environmental emissions. Turbine-impairing hiccups are a thing of the past, and electricity can be produced for approximately 4.5 cents per kilowatt hour. That's in US dollars. That's about 0.037 euros per kilowatt hour. Thanks so much for listening. I hope we've clarified, at least in part, why ZGE's sealed system geothermal offers a welcome innovation to today's conventional geothermal technology. If you'd like to learn more about ZGE's sealed geothermal technology, please pay us a visit at www.zgroupenergy.com. We'd love to hear from you.